Okay, well, yeah. I didn't record the audio for this in the first go around, so here I am again. I hate my life. Okay, so we're gonna look at pedigrees today. The genotypes going to phenotypes, right? A reminder that genotypes are the letters. I think at some point I draw those in. Can't really remember because my audio is not on my video. Anyway, the genotype is the phenotype, or the genotype are the letters, right? Whereas the phenotype are the physical expression of the trait. For example, for genotype, you could have capital R, lowercase r, right? Heterozygous. Or you could have something like, for a phenotype, the phenotype would be red, the actual trait that you see, right? Okay. So, we can skip some of this, and we're going to start talking about pedigrees. So these are similar to like family trees, for example, is where you might have seen one. So we're just going to go through some of the basic ideas of a pedigree, some important things you need to know about pedigrees. First of all, the squares, right, are male. So those are male individuals. And the circles are female individuals. So 1 would be male, 2 would be female. You can see that over the side in the key. We're also talking marriages are at one line that connects to, right? So from 1 to 2, those are married. 3 and 4 are married. 9 and 10 are not married, right? Because there's no direct line that connects them. Instead, they are siblings. They have that overhead line, right? The line that sort of goes over the two of them. That means they're siblings. So 10, 11 are married, 8, 19 are siblings, and they're the children of 10 and 11 because you can see that vertical line connects them. Hopefully some of this is familiar. Right, here's another example, 13, 14 siblings. They're the children of 5 and 6 who are married. 6, 7, 8 are siblings. They're the children of 1 and 2 who are married. And then the ones that are colored in are affected people, right? So that means that they have the trait, right? So if rather the trait is brown eyes, so all of those people that are affected for 11, 10, those people have brown eyes. And the trait is determined beforehand. Yeah, right? So here's my example. I think I said brown hair, not brown eyes. So we can say 4, 10, 11 all have brown hair. And 3, 12, and 9 do not have brown hair. Right, so 3 does not have brown hair because it's not colored in. So it'll tell you which ones, right? But that's why some of them are black and some of them are white. The black ones usually mean affected person, affected with whatever trait that is. And it's used to track those traits in different family trees. It's really helpful, pedigrees are. It's like a tool, just like the Punnett square. Okay, so we are going to go ahead and look at this earlobe pedigree, right, that compares free earlobes. And free earlobes are sort of unattached to the side of your head versus attached earlobes, which are more firmly attached to the side of your head. Right, so you see the attached earlobes over there. Okay. Well, we want to figure out, right? So the first thing we're going to write in, so we know that free earlobes are dominant, right? So they are dominant, and we're going to use E's to represent. So something that's dominant is a capital E, which means that the attached earlobe is recessive, so it's going to be a lowercase e. And you can see that in the key, right? So male with attached earlobe is colored in. So we know that the colored in ones are the recessive traits, right? So if you have attached earlobes, you are recessive, right? And you have to be homozygous recessive to have attached earlobes. So anything colored in is going to have attached earlobes. So we're going to go, and that genotype will be lowercase e, lowercase e. So we're going to go ahead and fill in those genotypes where we see them in our pedigree, right? So let's see if I do that. Oh, I'm going over here and talking. If you have free earlobes, you can either be homozygous dominant or heterozygous, right? So you could be capital E, or capital E, lowercase e, either one for free earlobes. But we know that if you have attached earlobes, you're going to be lowercase e, lowercase e. So I am going to fill those in at some point. Let's see when that happens. Here we go. So then go through the pedigree, and the first thing you want to fill in is those recessive, because you know for sure what that genotype is, right? You don't know what your dominant genotype is going to be, but you do know your recessive genotype. So if you go ahead and fill those genotypes in, that lowercase e, lowercase e. We wait while fill that in. So then we're going to see if we can determine some of the other genotypes as well. I'm going to close that. Okay. We're going to determine some of the other genotypes. So we're going to start over here with this couple, this married couple, and they have 4 kids. And they have 2 kids with attached earlobes, lowercase e, lowercase e. And I'm going to number those parents 1 and 2 just so they're a little easier to talk about. And like I said, 1 and 2 have 2 children that have recessive traits, but neither 1 or 2 have attached earlobes. So I'm going to go ahead and see if these, look at some potential genotypes of 1 and 2. So they could both be capital E, by capital E, but that does not, there's no way that can create any recessive because there's no lowercase e anywhere in there, so that can't be possible. So we know it cannot be capital E. Okay, we're going to put that in, right, because there's no lowercase e, so there's no way they can have any recessive children. That's not possible. Oh, what am I doing over there? Don't know. Okay, so we know that homozygous dominant for both parents is not possible. So we're going to try another possible 2 genotypes. Right, so another possible 2 genotypes could be capital E, capital E. Oop. Okay. For person 1, so homozygous dominant for person 1, and then heterozygous for person 2, right? So that could be our other genotypes that we could have. So we're going to make a little Punnett square to see if that would work, if that would create recessive children. So we're going to slowly plug this in. It's really painful doing these Punnett squares, drawing on my computer pad, but that's okay. So we're just filling in the Punnett square. So 1 parent on top, capital E, 1 parent on the side, E. 1 parent on the side, it's heterozygous, right? And then you're going to fill in your Punnett square. I'm sorry for the background noise. Nothing like working from home. And what we see is that you only have homozygous dominant or heterozygous, both of which would be free earlobes. So this pair can also not create any recessive or homozygous recessive kids, right? Like capital E, lowercase e, there's no possible way it creates recessive children. So that does not work, right? So now we need to try our last option that it could be. And that last option, I'm going over here and writing in what it can't be. I think that's what I'm doing. It can't be homozygous dominant, right? That doesn't work because it doesn't create recessive children. And we just did our Punnett square to see if this could be the two genotypes of the parents. And that doesn't work, right? Because we did our Punnett square and we don't have any recessive children. Anybody know why it can't be lowercase e? Because 1 and 2 are not recessive, right? They're not showing that attached earlobe, so they can't, neither of them can be lowercase e. They both have to be the last option, which is both heterozygous, right? Capital E, lowercase e, both heterozygous. Over here, I'm asking why they can't be lowercase e. It's because they don't have that trait, right? They're not colored in, so there's no way they can be that. That's not an option. So they're both heterozygous. We're going to do that little Punnett square, hopefully. Just wait while I fill that out. Okay, so the two parents are heterozygous, so that goes on top and bottom. And then we have one child homozygous dominant, one child heterozygous, another child could be heterozygous, right? I'm getting a little lazy with my writing here. And then finally, we do have the chance that a child could be recessive, right? So we see that, which means that because that's the only genotypes that could possibly create recessive children, those have to be the genotypes of 1 and 2, because you see that recessive child is a possibility, and they have recessive children, so they both must be heterozygous. So what we've done there is use the pedigree to figure out other genotypes in the family tree, and that's why pedigrees are useful. Again, we're using that Punnett square as a tool as well. So I think I'm going to circle. Yep. Okay. So this when the children, right, also create a recessive child, we could also figure out those two children because they have a recessive child and they're both free earlobes. We know they also must be heterozygous, because that's what we just figured out in our previous little marriage with children, and they're showing the same thing, right? So once you sort of figure out the patterns, it can be easier to figure out the rest of the family tree. Right, so I don't know what I'm doing here. Okay. Then I'm going to go through the steps, right? We've filled in the recessive individuals first with our little e. And then we went in and filled in the dominant alleles because we know it has to have one capital E, and then the other allele could be lowercase or a capital, right? So that's what we figured out for number 1 and 2. And then we deduce or figure out the rest of the genotypes, so whether or not that's capital E or lowercase e. Okay, and I think that's all there is for pedigrees today. We will see if the video goes any longer, but that's what I'm thinking. Yep, that's all there is for pedigrees. So hopefully the problems will be easy.